Okay. Hello, everyone. So today we're going to go deeper into the concurrency model of Altstore. And so in particular, we're going to look at the topic of index maintenance. We're going to look at multiversion concurrency control. And we're going to look at the coordination-free aspect of that. And then some of the lineage-based storage architecture, sort of the section 4, that was something that was already covered 2 weeks ago. So we're kind of going back and filling the gap before getting to the storage. So the storage we've already covered. We're going to kind of paint a whole picture, looking at the concurrency aspect of the L-store. And then I'm going to give you some sort of next step as well too. So in the next few set of lecture, I will give you sort of what's about to come, sort of what is the next sort of big thing in this field. So that I will cover it so you kind of have a nice vision of where the database community or the database research is headed to. So I'll give you some intuition into that as well too. So this problem of index maintenance, which is, we're going to formally define what it means. And this is where the idea of indirection, at least in L-store, was really when it started. So that's the kind of the seed of the whole L-store design. It starts at this indirection and starts at this index maintenance. And so what is an index maintenance problem is that in particular, so a basic problem that we kind of look at is if we assume that we are building this operational databases, and by operational database, as we mentioned before, is a database that allows us to do both analytics and transactional processing. And if you wanted to kind of do more sophisticated analytics, one thing that we also wanted to do is to be able to maintain all the versions of the records. So this allows us to see the evolution of the record. It allows us to gather more insight of how the data changes. So that's an important element to keep. So if now want to maintain all the version of the record, there is two kind of design choices. One is, broadly speaking, is that I have a latest version of the record and I have all the earlier version of the record. So I can design my storage layout such that I have one location that I can, in that particular location, I always keep the latest copy of the data. And then I have like a trail that I store the earlier version of the data. So that's kind of had been the standard way of dealing with multi-versioning. But in the L-store, we know that's not the case, is that I do have a sort of a stable version of the data, but then any changes to the data gets appended to the tail pages. There's no in-place update. And periodically, we'll take those accumulated update and apply it to that stable location. And this helps us with an array of problems with regards to concurrency. So now, if you're not doing an in-place update, we're doing a multi-version, there is an issue that one has to deal with. If you're constantly changing where the record is pointing to, then that means your reads or your location of the record will continuously change. And that means all your indexes need to be modified. Because every time if you're creating a new version of the record and indexes are pointing to physically using read to where the record resides, then they need to be changed. So that's the problem of index maintenance. And so here again, and some of this have already been actually incorporated, and so I'm kind of giving it a different view. You've already seen this implicitly. So in order to deal with this index maintenance issue, we kind of can envision this storage hierarchy that we've also been repeatedly talk about, is that the storage hierarchy, we have main memory, we have SSD, we have disk and potentially tape, and perhaps even other devices in between. So if you imagine this extended storage hierarchy, then what we would like to do is that in order to address this problem of index maintenance is to decouple the logical and the physical location of the record And this could nicely blend into that storage hierarchy. The physical location of the data could be on disk. This decoupling of physical and logical could be in mid-tier, for example, on SSD. And then finally, the actual logical pointer or the indexes would reside in main memory. So that gives us a way of also in which memory tier or in which storage tier we're going to store various pieces, But be a little bit more specific, again, in the context of index maintenance. So this is what traditionally databases will have, which is you have what it's called read indexes. And what read indexes is that when the indexes, they have the key and they point to the actual physical location of the record. So you see these indexes are directly pointing to the pages that are maintaining the record. So you could think of that these are 3 different pages and containing each color, let's say representing a different record, and the number is different version. And kind of for simplicity, assume each page contains a single record. So we have 3 records, you have blue, red, and orange. They're all on version 1. And when we have read indexes, all the indexes are directly pointing to the physical location of the record. So this could be an index. If this is kind of a student relation, this could be an index on age, for example. This could be an index on name, for example. And you could have all different kind of combinations of indexes. We have composite indexes, but at the end of the day, index has a key, whether it's composite or not composite, and contain a read list, as we had previously discussed. And so that means the reads are pointing to the physical locations of these records. So is that clear? So that's kind of our basis. And we're going to kind of really build incrementally on this, and we're actually going to see how the simple design that we're talking about is actually become the basis of LSTOR. So that also you see the progression and development of the idea that have led to LSTOR. But this is the basic. This is the most basic aspect of it.
Professor, I have a question.
Yes, please.
So you said that the index maps a key to the physical location of a read, so the page range, the page, and the offset. But doesn't our page directory already do that?
So first of all, here, we're talking about it abstractly. There's no page range. We're not talking about LSTOR here. Right now, we're just talking about basic. So if you remember what read is page ID and slot ID. And that's an abstraction that is also applicable in LSTOR. So read is a page ID and slot ID. Now, if my page ID is itself logical, I cannot use my page ID to physically locate where my record is, then I would need a page directory.
Okay, I see.
But when we talk about indexes, the indexes have read. So now this read, using the read, I can physically find where the record is. I may have to do some other steps in between just because I'm given a page ID of 50, but then I ask for where is actually page ID 50 is. So that's another layer of translation that needs to be done, and that's done through page directory. But from the perspective of the indexes, you have key and set of reads, or a single read if it's a primary key index.
What was the last part? Sorry.
So if it's a primary key index, then for every key there's only one read. So if
okay, yeah, exactly.
But if it's secondary index, as we talked about, then for a single key you have a list of reads.
Yes.
But irrespectively, given a read points to, given a read, you can physically find the location of the record. You can physically look it up. To do that lookup, you may need another lookup to kind of translate page ID to actual physical pages, and that would be your page directory.
Okay, thank you. Yeah, just wanted to confirm that.
Perfect. No, that's a very important question. So is that clear for everyone? Okay. So now let's see what happens. So now if I'm doing multi-versioning, and I want to retain all the version, and I want to avoid in-place update. And this yellow stuff is the hard disk. This just the entire kind of abstract view of the disk. This yellow things doesn't mean a single page. This yellow thing means just the entire hard disk space. So again, we don't want to do in-place update, and for the many reasons that we've already talked about in LStore as well too, we don't want to do in-place update. So that means if I'm writing a new version of the record, somehow I'll create a new version. So now if I'm creating a new version and writing it somewhere else, so this, the act of writing a new record essentially changes a read. This new record has a new read. So now what needs to happen is that all the indexes need to be updated. And if the index is only indexing the latest version of the record, they all need to be updated to point to this new location of the record because the read has changed. So you need to go back into your indexes and update the read. Even in LStore, when we're adding records to tail pages, what we're essentially doing, every record in the tail page is a new read. So every time we write something new in a new location, we are generating a new read. So what the default model of a database would do is that every time a new record is generated, every time a new read generated, they would have to go and update the indexes to point to the new location. So that's something that would happen. Traditionally, this is what something would happen. And even today, this is probably the most common way of things being implemented. And so what that means, for every single update, even let's say the update, it was an address. So I changed the user's address or the student address. Indexes are not even defined on address. One is on name, one is on age. Even the indexes that were not even affected by the updates have to now go ahead and to be updated. So that means lots of random accesses, lots of things need to be randomly updated. All these indexes needs to go, you go through the tree and potentially have an effect even on the non-diff structure of the tree. All of these have to be locked partially for that update also to go through. So lots of changes would happen as a result of doing a simple creation of a new version. So now the idea is, if I now change the blue record, same thing will happen. I create a new version of the record, a new read is generated. That means all the indexes, these are read-based indexes, needs to go back and be updated. Make sense?
Professor, could I ask something related to the Ulster, but also regarding
Sure,
the index?
absolutely.
So you said that every time we update something or we need to like update the index. So does that mean that we're only going to that specific index of a certain column and we're mapping one of the keys to the new generated read, right?
Yes.
So in that case, do we just keep the old key mapped to the base record or to the previous read before the update, or we also have to unmap the previous version of the record and unmap it from a certain key?
Yeah, so that's a good question. And there is no necessarily a right or wrong answer here. It's more on the use case. Typically, indexes used to index the latest version of the data. That means the version 1 of both the blue and red record, we typically don't want it to be indexed because there's not much use cases of using to find the earlier version of the record through the indexes. So therefore, we will kind of have to remove it. So not only we have to add the new version, add the new version of the record where the new read is, but we also want to remove the old version because otherwise the indexes keep getting bigger and bigger and bigger as well too. So that's a typical setting. You usually remove the old version from the index. The data is still there, but the index is not pointing to the old data. The index are only maintaining the latest version. But again, there might be an application that you say, well, I really want to be able to have index my history as well too. And you can use a standard index to fulfill that need as well too, but probably you need something more optimized. If you want a index structure that allows you to index the history, there are more interesting, clever optimization that can be done as opposed to just kind of just basically keep the old version around. So there are better ways to handle that. So that's now we have to look into optimized form of indexing for multiversion.
Professor, I understood, but what if you only like had to store the index from the very first from the base record, store that index, I'm sorry, that read, just store the read of the base record, and just every time you want to go to the most recent update, index like index some key and get the base read, and then through the indirection column go to the recent update.
Exactly.
In the case of the All-Star.
And that's where we're going to, and that's where we're coming to. So that's exactly so this is the idea of that indirection. So that's how that idea of the indirection came about. Exactly what you described. So this is exactly the next step. Exactly. And that's why it adapted itself. So we see in the L-star, that indirection column. So this is the evolution. So that's how it came to be. These are the reason, and that's how it kind of expanded into that model. So we started saying that I want to maintain multiversion. I don't want to look at in-place updates. Then I have an index maintenance problem. So now the question is, how do I solve my index maintenance? Then I kind of ask, well, so we now fixed the index maintenance problem, but I have multiversions. Can I improve my concurrency? Okay, then we kind of look at concurrency. Then I say, well, I have multiversion. I solved the index problem. I improved the concurrency. How do I deal with the storage? Can I now also improve this from the storage perspective? And so far we've been talking about, we kind of look at that sort of the third step, which is the foundation of storage. Now we're kind of coming back up and say, okay, well, there was also index problem and there's also interesting concurrency problem. But I wanted to kind of first lay the foundation of the L-star from the storage perspective so we can get the first assignment and the second assignment going, and then coming back to concurrency issues, because a lot of these things that we're going to talk about is about synchronization and concurrency. So that's how things are slightly different in the order that we're going over it.
Okay, thank you, Professor.
Thank you. So exactly what you said. So we're going to visualize the idea that you just shared with us. So basically, we have read indexes that point directly to the version of the original version of directly point to the version of the record or the latest version of the record. Now imagine we kind of decouple that. So decouple the physical and the logical location. So we add this layer of indirection, this layer of mapping. So now the index has become lit. So every record will have a stable read, or another word, have a logical identifier, and the indexes only maintain this logical identifier. And from the logical identifier, we can map to the latest version of the record. And this logical identifier, for example, in case of L-star, we say this logical identifier is the base read, is the original read that we assign to the record. That becomes that logical identifier. And from their points on, every single index only points to that base read. Every index points, another word, alternatively, you can name it the logical identifier, because that original index, that original location, it's logical in a sense that there's so many other versions that is happening, but it becomes a stable point. And the logical identifier is the definition of that stable point. So now, if I'm changing a new record, so again, when we're talking about here, there was no L-star. So L-star is something that was developed 2-3 years after. So so at this point, when originally I want to change my read record, kind of rerunning the same example, it was pointing to the first version. Now, if I write a new version, I kind of append only a new version, the version 2. But before, we had to kind of go back, change all the indexes. But now the only thing that needs to be changed, a single location in our indirection mapping. So now we have an index, we have indirection mapping, we have our data. And in the indirection mapping, we maintain the pointer to the latest version of the record. Of course, this indirection mapping is sort of implicitly becomes a column later on in ELF-STOR, but this is how it was initially sort of manifested itself. So it was seen as indexes, this like a hash table, as think of it perhaps a hash table or just yet another index structure. And this index structure, it was a mapping that gives you translate a lit to a read. And of course, once you have a read in hand, depending if you can make sense of that page ID directly, then you can go directly to the page. But if you can't, then you also need a page directory. So potentially yet another level of mapping. You want one more level of mapping is that once you have, once you got your page ID, you translate it through the page directory to the actual physical page. Now you know where that physical page is. Now you want to see if it's in your buffer pool or not. And then you have to kind of map it to a frame into a buffer pool. So you can think of it as yet another lookup or another indirection, from index to indirection to page directory to a frame in a buffer pool. So that's, you kind of flow that to actually finally find that page. So when you look at implementation detail, and again, of course, it depends on how one implements it, but that's one potential path that you can go through. The blue record, I add a new version, I append a new version. All I need to do, change, update my my indirection entry. And again, you can think of this is that these are later on, what we talk about, these really becomes our base pages. These really becomes our tail pages. And now we're kind of pointing to the latest tail. And this becomes a column of our base page. So that's how then later itself, it kind of transforms in ELF-STOR. But this is the way, this is how we got started. We were solving this simple problem of index maintenance, is that I'm adding a new version of the record. Index isn't physically pointed to the record. Now, if I'm keeping a multi-version, for every new version of a record, I need to go change dozens of indexes, even if those indexes are not related to that change. So that was the sort of the initial entry point into this problem. Does that make sense? Any question on that? Okay. Again, I think experiments is important. Every time we want to kind of looking at a new design, we need to look at it analytically and experimentally. I'm not going to go really into detail here, but from an analytical perspective, we can kind of look at updating, let's say, a single attribute using a base technique, sort of a naive or the standard approach. This is not, doesn't mean base page, this means base approach. Or using an indirection, using a single attribute update. Of course, we can look at deletion, we can look at insertion, we can look at lookup, and we can really look at different parameters. We can also, depending on how the data is related on disk, whether we're using SSD and disk or not. And then we could also further differentiate what action needs to be done immediately versus what action can be sort of delayed. In the background, eventually I can, for example, do a read or write to SSD. Again, that's kind of done for both SSD and disk. So that's kind of really going detail into the analysis, but kind of at the high level. We're going to look at this at a little bit of high level. With the standard technique, if I'm doing a single attribute update, then what I need to do, and forget about the 3 and the 2, those becomes a bit involved, and forget about the immediate and deferred, that also gets a bit involved. But the basic idea is, if I'm doing a single update and I have k number of indexes, then the number of operations that I do on the hard drive will be minimum would be in order of k, minimum order of k, because assuming that my indexes, usually my non-leaf pages are small enough fit in the main memory, but the final layer usually would result in a cache miss, so potentially access to a hard drive. So now if I am updating k indexes, and these keys will be randomly distributed in those different k indexes, and I'm going to hit at least one leaf page of those indexes, and there are k of them, so at least there's going to be k random accesses. Well, with the indirection, of course, we eliminated the k. And if this is a single attribute update, and further assuming on each attribute there's no more than one index, then, well, there's only one index that needs to be updated. If there are k indexes, but only one of those indexes are relevant to my update, because I'm only updating a single field, and there's only one index defined on that field, then the number of changes that needs to be made in terms of the number of random accesses will be constant. But in the base approach, even if I'm doing a single attribute update, even if I am only having one index defined on that attribute, I still have to go change every indexes because the read has changed. So that's the sort of the basic intuition that we've already seen it in design. So now here, kind of looking at it more precisely and more formally, and really actually doing accounting, really go and counting every single step of the way. But again, that's important. When you think of a new design and new optimization, we want to be able to look at some form of a complexity analysis of it. So that's their step analysis, or the time complexity, in terms of what's expensive, and that's first is the accesses, random accesses to the hard disk, and then the random accesses to SSD, and the cost model will be driven based on that. Any question? So now let's it's important to also look at experimentally, because then also it's good that you learn how to think about the problem, how to set up your experiments, what kind of experiments you want to run, and what's the setting is. And I think coming up with those parameters are non-trivial, because you really want to be able to show a set of experiment that captures the key benefits of the design. So in these experiments, again, these are kind of older. This is around 2012. Most of these were done. Is that we're using an Intel machine, has 2 sockets, each with 8 cores, and about 32 gigabyte of memory. And some of these approach were actually implemented in IBM DB2. So they were directly implemented in DB2, which is, has millions of lines of code. This is a fairly sophisticated, not fairly, it is a very sophisticated product. And also some of the techniques were kind of done in a proprietary database for confidentiality, they cannot be named. And we also looked at sort of open source, like Apache Spark. I don't know if any of you are familiar with the MapReduce and later Spark, so that was also looked at. And the list goes on. So it wasn't just implemented, okay, let's just do it in DB2 and let's see if these approaches are effective. We're kind of looking at 4 or 5 different software and implementing those and see the effect of it and see how effective those approaches are. And so that's in terms of hardware. This is the software used. And now we also have to talk about the data. What kind of a benchmark that we use? There's one standard benchmark called TPC. So TPC are standard benchmarking databases. And so all the major vendors use them. And TPC-CH, with the ending with the H, this is an analytical benchmark. So it really focuses on complex analysis, complex queries to run reporting. And then there is also a Microsoft micro benchmark that is kind of really focused on queries and transaction. And this benchmark was proposed as part of this Microsoft Hackathon product. This Hackathon product came out around 2010, 2011, and it's an in-memory transactional store. The focus is not about analytics, it's try to do just really fast in-memory an in-memory database. So let's see what is the effect of this. So kind of taking a step back, here we say we have our TPC edge, so it's a pretty sophisticated sort of workload. We create all the tables that it needs, and it has these complex queries. These queries could be like pages long and with many joins and very sophisticated. Now you say, okay, what kind of indexes I need to create? Most databases also have this index advisor. So you kind of give the workload, or especially the queries, given a set of queries, it says, okay, if you create these set of indexes, we'll optimize your workload. So it gives you some suggestion. So now the interesting thing is, here you say, okay, the base thing is to have one primary key index. So there are 7 tables in this workload. Let's have one primary key index for every table. So that's our standard. And then start adding more indexes. So kind of following the index advisor, it's suggested to add all the way up to 17 indexes in addition to that 7. So 10 more composite indexes, which is indexes on pairs of attribute, as opposed to the primary key, which is just on a single attribute. So it's suggested to build the 17 indexes, okay? So now the first experiment is that, well, if I have these 17 indexes and I'm going to maintain all the version, what would be the effect of update? And we see the cost of update, and these are sort of the relative cost of update versus the indirection. We're not showing any absolute number. Is the cost of update for indirection roughly remains about, so for the base technique, it gets to 1, it's like 100%, because that becomes our baseline. So with the indirection technique, even as we increase up to 17 indexes and generating random update workload on these 17 indexes, it remains about 40–50% of the cost. So it allows us to save, let's say, 50%. In the beginning, when there weren't that many indexes, the cost was much less. I mean, the benefit, the gain was a lot less. But as you add more indexes, this gain becomes larger, larger, and larger. So with 17 indexes, the overall cost of update has gone down by at least 50%. And this is running in DB2. This is running, we're running a real database here. And the size of the data, scale factor 20 means the size of the data is 20 gigabytes. Okay, so that's good. So we know that indirection is improving the update. But now the question is this the whole story? Is there anything else more to this story? And the question is, well, what happened to the read performance? So now we look at the query performance based on indirection. And we know with the indirection, the query performance should be penalized, because with the base, I can always go to the latest version directly from the indexes, but with the indirection, I have to go to that additional level of mapping. I have to go from base, I have to go from the index, go to indirection, and then finally to where the actual physical record is. So how does that translate to? So the blue is the base approach, and the indirection is that the red. And we see it's about 10, 15, maybe even, yeah, about usually 10 to 15% overhead in terms of having this indirection layer. But now here is what the interesting point is happening. As we add these 10 more sophisticated indexes, forget about this sort of the penalty here that is about maybe about 5% overhead of doing an indirection lookup, putting that aside. As we start with basic, just the primary key, and going up to 17 indexes, adding 10 more indexes, as we do this, the overall analytical performance goes down by nearly 70%. So adding more indexes allow us to go down 70% in performance. Okay, which is noticeable. It's very important. Indirection adds a short additional 5% overhead here. That's okay. But the key is, the only reason they could actually add these 10 indexes was the fact that they had that indirection, was because since we were able to reduce the price of update by 50%, then we could add all these indexes and get that 70% reduction also in the query performance. So again, the indirection not only reduced the performance of the update, but since it reduced the performance of the update, it allows us to add even more indexes. So it wouldn't affect our transactional workload. So it would allow us to add more indexes, and as a result, get 70% improvement on the analytical performance. So again, that's the point. Is really want to be able to develop this operational data store. The point that we want to be able to create this edge tab. We want to be able to do analytics and we want to do transactions. And that's the first key sort of a result here, that showing that this indirection that was really focused on update, well, you can have more indexes, and you can have more indexes, you can also reduce your throughput substantially. And also you have the ability to look at historic data as well too. So that kind of be the added on benefit. So that's how the work of the indirection and the index maintenance sort of began. And of course, as we've noted earlier, some of you noted to this becomes later on, this indirection mapping, as opposed to being an independent structure, becomes as a column of table in LStore. But that's kind of its evolution. So that's where it came from. And so that's now, I hope you have a better understanding of the importance of that layer of mapping in terms of data structures. Any question before we move to the next section? Okay. So now let's look at concurrency. So this is kind of the next aspect to look at. So we look at index maintenance. Now let's look at concurrency. Again, let's kind of start with our same problem statement. And again, it's important to create those problem statements to allow us to guide our thinking. So problem statement here is, in this operational multi-version data store, there is this tremendous opportunity to avoid clashes between the readers and writers. And the readers are kind of reading large volume of the data, and the writers are doing frequent updates. So that's the observation. So there is clashes, and the question is, how do we try to eliminate or reduce the clash between readers and writers? So that's the problem that we want to focus on. And the idea here is that in the indirection, we created this layer, this indirection layer, to decouple the physical and logical location of the record. And that allows us to avoid the problem of index maintenance. So that's what we did in the indirection. Now we're saying, can we create a two-version concurrency control? So if you look at our standard 2PL locking, is we always assume that we only have a single version of the record, and that's the latest version of the record. But can we create a two-version concurrency, a variant of two-phase locking that exploits the idea of the indirection? And what is the aim here? Is that in the same way that with the indirection, we try to decouple the physical and the logical location of the record, we would like to decouple the reader and the writer of the data, the transactional update versus the analytical reads, to reduce the contention. And then we want to look at this at a very sort of a general and broad perspective. We want to have a variant of the 2PL, a variant of the two-phase locking that requires at least two versions of the record, as opposed to just be limited to the latest version of the record. But we also want to have the options of looking at optimistic versus pessimistic. And you want to kind of do it perhaps in a unified way. So how do I exploit? I have maintaining multiple versions. Let's assume that I have access to two versions. How do I exploit that in my concurrency to eliminate the contention between the read and write? And also, how do I navigate this optimism and the pessimism of locking? Can I kind of bring that into one unified model? And so we're going to go in sort of in detail on all of that. But that's the goal here. Any question? let's look at this simple idea of the indirection, which is the basis of everything that we've talked about so far with regards, of course, to the indirection technique, but it's also the basis for outstar. What was it? We said instead of having read indexes, we will have lid indexes. The lid indexes point to this stable read, or also calling it logical identifier. From this logical identifier, we point to the latest version of the record. So that's the basic idea of the indirection that we've been talking about. Now imagine expanding our indirection, adding another layer to it. And so the base, so this indirection, instead of just having a pointer to the committed version of the record, which we can call it, let's say, C-read, a committed record or a committed read. We also have another sort of, let's think of it, another column here. And this column could be the URID, the uncommitted record identifier. So from the indirection, I can find the committed version of the record. I can also find the uncommitted version of the record. Okay, so now let's rerun our example and see why is this useful? Why is this something of interest? When I'm adding a new version of the record, when I'm changing the read record from version 1 to version 2, so what I need to do is, since I have an uncommitted read, this is the version of the record. So the transaction is started, it has updated a read record, and it may want to update other records and may do other things. Maybe that's the first step of the transaction. So at this point, this version of the record, although it's written and recorded, it's not finalized. And we talked about, for example, the concurrency anomalies or the transactional anomalies of reading an uncommitted read or an uncommitted record. So maybe for some application, it's okay to read an uncommitted record, but for some application it's not, and you kind of set yourself at the stronger isolation guarantee. But irrespectively, now from the indirection, we specifically track where is the uncommitted version of the record is. So what we did, we add a new version of the record, but we tag this as uncommitted still. So now, looking at this, can you begin to see opportunity to start decoupling the read and the write of the data by this structure? Can you begin to see some potential opportunity here?
I guess the original, what is it, the committed rids, those are only going to be for reading, whereas the uncommitted ones only for writing.
Exactly. So right now we already see the reader could follow a different path and the writer can follow an alternative path. So already there is that decoupling and the separations of where the reader and the writer will go. So that's the first step. Now, once this record gets, record 2 gets committed, so what we can do is to update our indirection, get rid of the URID or set the URID to null, and then this becomes our committed read. And now assume if I wanted to add yet another version of the read record, I'm going to write the third version of the record. And now my URID will start pointing to this newly uncommitted version. Of course, if the transaction comes in and they just simply are interested in reading the record, they can follow the committed and they can get to the second version of the record. Okay. But a lot of interesting things can happen here. What does it mean? I mean, we kind of mentioned this. Let's kind of make a simpler diagram here. If I am a reader, I can come and follow this and get the first version of the record. But assume this already a transaction that is already trying to change to and have written an uncommitted version of this record. and that transaction hasn't finished, is ongoing. Now assume a third transaction comes and also wants to change the read record. Then what can happen here? What can be utilized here?
Wait, I'm not sure I understand the question.
So there's one transaction that is written the second version of the read record, okay, and so it said the URID, okay, so that's ongoing transaction. Now in a second transaction, so this is, let's call this the first transaction, and a second transaction comes and wants to read the read record. Okay, well, second transaction can follow the committed read and read this record, okay? And they're going to come back to the second transaction. But now let's say there is a third transaction. This third transaction also wants to write to modify the read record. So what can we do at this layer? Is there anything that we can already be able to, what can be identified here? If you're a third transaction, try to write something. When you look at this setting, what can you conclude?
We should commit the second transaction.
Well, you don't have control in other transactions, as from your perspective, from the perspective of the third transaction.
I mean, because we're gonna update it anyway, wouldn't it be better to just run the third transaction first and then with the previous value, return it for the first two?
Well, that's a good question, but then that's kind of now saying the third transaction is going to read an earlier version of the record, and then it's going to write its own version and potentially overwriting this update, and then they're going to lose this update. Because this transaction also looked at the previous version and perhaps based on that previous version is write something new. So then we're definitely going to get write-write conflict, and there could potentially be lost update there as well too.
Wait, so the first two is just reads and the third one's an update, right?
No, so this is also update. This is the first version of the record. This is the second version of the record. The second version of the record is being done by a transaction, and let's call that transaction one. So transaction one is writing this new version of the read record, and it's ongoing. Now another transaction comes, that transaction just wants to do read, so we can say, okay, you go ahead and read the read record and kind of continue what it's doing. But yet another transaction comes, this transaction now wants to again write to read. I want to write a new version of the read, but the first transaction is still active and still has this uncommitted version of the record. So what does the third transaction can do here?
Delay execution until it commits.
And how does come to that conclusion?
Because it just looks to see that a URID identifier exists.
Exactly. So from the indirection now, this is a signal that, well, there is an outstanding write that is happening, and you can use this information to essentially communicate with other transaction that something is happening right now. And we could do that communication without actually holding a lock. Without holding a lock, by basically writing to this entry, it becomes a flag that there is an ongoing update happening for this read transaction. So instead of kind of holding a lock, this could potentially become an alternative way of doing that flag, saying to the third transaction, be careful, there's something is happening already. You can't really change this. There's already an uncommitted record. So you either have to wait or you just have to abort and say, okay, I cannot continue any further.
Wait, another question is, what if
Yes.
the second transaction wants to read the first one? Like, say, because it's still ongoing, and say like the user still just wants to read the most updated thing, would we wait then for the commit still to go through?
Yeah, so that's becomes a yet another very interesting question. So, so first of all, it becomes the isolation semantics. So it becomes the isolation level. So if that transaction, that reader transaction, is okay to read uncommitted data, then yes, it now can actually go and read the latest version of the data. But there's the caveat is that if it's okay with reading dirty data, it means that it is possible that it reads this version and later this transaction gets aborted and this version gets vanished. And as long as from the application perspective, it's okay if you kind of read something because you're reading so much volume of data. You may be reading 1 million records, and sure, out of that million record, if one or two kind of don't last, it's okay. You're still kind of getting an analysis, you're kind of getting an average, maybe it doesn't matter. So as long as the application can tolerate reading an uncommitted data, which later doesn't go through, then yes, so now we can directly allow it to read. But there's another interesting thing that can be done here too. So first, as was mentioned, the fact that we are writing here, the fact that this URID is set, it's an indication that there's a potential write-write conflict and there's an outstanding right. But here, we can also do something even more interesting, is that as part of this entry, we can also write a read counter, almost like a pinning the pin count of the buffer pool. So we can say, if I am a transaction that I'm already reading the second version, and then there is a new transaction that's writing the third version, and if I've read the second version already, I'm going to write in my URID, maybe I can allocate few of the bits of the URID to keeping a counter of how many outstanding reads are there. So in that counter, I write that I've read the second version of the record. And as long as that counter is non-zero, meaning that this URID now not only maintains the fact that there is pointing to the latest uncommitted version, but it also internally maintains how many outstanding readers exist, then it will not commit this write as long as there are those outstanding readers, because it says the outstanding reader are expecting this version to be the latest version. So I cannot finalize the version 3 as long as there are transactions who read the transaction, who read the version 2, and they think the version 2 is the latest. Once those readers are complete and that read counter becomes 0, then I can go ahead and finalize this version and essentially commit this version without violating that repeatability read anomalies that we discussed. So one of the isolation anomalies that we covered last time, one was write-write conflict, the other one was repeatability, meaning if a transaction read the read record at the beginning and reads the read record again at the end, they always should read the same value. That value shouldn't be changed. And if you are doing a serializable schedule, meaning that when there is the schedule is equivalent to a serial, in a serial schedule, because you're doing one action at a time or one transaction at a time, and then there's no way that if you in the beginning of a transaction you read something and at the end you read it, it changes it, unless you've changed it yourself, because there's no other things are running. So that under serializability, the repeatability is always preserved. So now one way of preserving that repeatability is that when you following the committed read and reading the committed read, you also write down or you increment the count of you as a reader that you're currently reading the latest committed version. So that means if the writer comes, it's okay. The writer can go ahead and actually write the new version, but it cannot make that version committed as long as there is an outstanding reader on the second version. So not only allows us to separate the readers and writers, the reader goes one path, the writers goes a different path. It allows us to potentially detect write-write conflict, but by allowing us also to hold the read counter, it could also help us to eliminate the read repeatability as well too. So that's another thing. So now all of those anomalies of all those things that we wanted to kind of capture, we see, okay, now we can actually implement it. This very simple idea of indirection, now it's kind of, we see its different capability and different ability or potential that it has, that it can help us to actually now construct a whole, using it as essentially a data structure, not only a data structure to help us with the index maintenance, but as a data structure to help us to actually implement concurrency protocol.
I guess I'm not seeing how, because to me it seems that like the implicit indicator of write-write conflicts, like in a sense, it's like very similar to latching. So I'm not seeing like where that deviates from it.
So this becomes a way of implementing that idea of latching. It is the notion of a locking, but it becomes, you still have to say, how am I going to implement it? What is the best way of implementing it? Am I going to maintain a whole different data structure to kind of maintain my lock table? I'm going to manage what is being logged. So you still have to implement it somehow. You still need variables, you need data structures, you need maintenance, you still need to maintain it. Now you're saying, okay, can we just use this data structure to also to serve that purpose as well too, to allow us to implement even just the basic idea. Well, it can't really do two-phase locking in fully, because two-phase locking has two flavor, and kind of we talked about that flavor here as well too, is the idea of the notion of waiting is one that I want to be able to lock something or latch something. If it's available, I can write down my name and go ahead and start being the owner of that. But the other things that locking could provide is that if I want to do something, if I want to do a write, then I also need to kind of, if that resource is not available, then I need to kind of wait for it to become available. And one way of waiting for it is to construct a queue. So I maintain a queue, and for that particular item that I want to lock, I add myself to the queue, and that queue kind of manages or invokes me or informs me whenever that resources that I was waiting for, it's my turn to go ahead and change. There also may be a way of, I'm a transaction who are doing this change, and I kind of spin lock on it, what they call it the spin lock. I kind of loop on that. I keep checking it. Is the URIT sit? Is the URIT sit? Is the URIT sit? Is the URIT sit? And I kind of could potentially continuously do that till I get to the point that the URIT is not set, and then I can continue. So that could be another form of waiting. So again, the locking itself, the 2PL locking, has different components, and all of them can be implemented here, but the mechanisms are different. So especially the waiting mechanism needs to be adjusted. And the other interesting that has also happened at the same time during this sort of now kind of putting this work into the context is that given most of the data are often found in main memory, the memories are getting larger and larger, then it makes sense to, well, since the data is in main memory often that you can find it there, the cost or the duration of the transaction becomes shorter and shorter. So the cost of executing the transaction becomes a lot less. Now the question is, if a transaction is hitting a wall, and that's because the data is not available or for whatever other reason, it's now much cheaper to just abort the transaction and retry it later. So if the transaction cost is a lot less, the abort cost is a lot less, and one may say, well, maybe we don't even need to wait. So all we need to do is we have a non-blocking protocol, meaning in a sense that if I want to write something, and if I detect a write-write conflict, I simply abort. If I want to write something and I don't detect a write-write conflict, I'll continue. And we don't need to worry about having those wait queues and so forth. And so that was another change kind of happening in the background. But with this structure, you can, so once you go into details, we can handle all those flavors. So we can handle all those flavors as well too. But again, so that's again more contextual background on this. So idea, again, kind of wrap up this figure because it's important. So we have URID and a CRID. We distinguish between our committed and uncommitted RID. The reader always follow the committed RID. The writer always follow the uncommitted RID. The uncommitted RID, the fact that it's not null is an indicator there is an outstanding write. In the uncommitted RID, we can also write, have a sort of an internal counter to be able to count certain number of outstanding readers. And as long as there's our outstanding readers, that could delay or prolong the time that the writer can go ahead and installs or commits its write. So it will help us to help with the repeatability anomalies. So the write-write conflict can be determined by the fact that the URID is set, and the repeatability can also be eliminated by having the notion of the read counter. And of course, it's the structure on its current form, it's really, it lends itself really nicely with this non-blocking approach. Is that if what I need to write to, if I need to get a write lock or an exclusive lock, and that's not available, I simply abort and retry. You can do the other approach as well too, but it lends itself really nicely to that basic observation that abort is cheap, let's not do blocking, and let's just simply move on. So now, okay, any questions, any more questions before I kind of go to the next part? Okay, so let's kind of now revisit so we looked at the data structure. So we want to use this structure to essentially implement two-phase locking. In fact, here is now two-version locking. This is 2VCC, not two-version locking, two-version concurrency control, because it allows us to read both the uncommitted and uncommitted, and it allows to access both the uncommitted and the committed version of the record, and that's where the two version come into play. And the whole protocol just requires this two version. With that two version, we can kind of do all of these concurrency improvement, as we mentioned. So overall, let's look at the two-phase locking. So visually, what was this two-phase locking that we discussed last time? There is a growing phase in which you acquire lock, and then there is a shrinking phase that you drop lock, so you release lock. And the only criteria that 2PL is based on is that if you begin releasing lock, then at that point on, you can never go back and acquire lock again. As long as you satisfy that, then you can show that the protocol, then you can always get a serializable schedule. So as long as you enforce that you never start releasing lock and then reacquiring lock, then you can be serializable. So always acquiring, and then strictly acquiring and strictly releasing. And that's why it's two-phase. And some of the lock could be exclusive or a write lock. Some of the lock could be shared or read lock. So the exclusive is where all the blocking happens. If I'm holding a shared lock, then all the other transactions who just want to be a reader there's no contention. So the green region is our shared region, which is good because as long as I'm in the green, that means everything can go concurrently. The moment I come in the sort of the red region, well, it becomes exclusive. That means concurrency is reduced. Potentially only a single thing is moving forward. So now what the two-phase or the two VCC looks at, it says, okay, I had this growing, so I have this exclusive, I have this shared lock, potentially have a growing phase and have a shrinking phase. But what if I introduce yet a new phase and call that a certified phase? And so this was you can think of this could potentially be our commit point. And we said if you want to avoid cascading a board, is best to just keep the locks up to the commit point, and at commit point just release them. So you can think of this line as also our commit point. Now we say I have my commit point, but why don't I also add a certification point? And why is that useful? If I have this certification point, then what if I just start by holding shared locks? Even if I'm a writer, I simply just hold the shared lock. So when I start, I get shared lock for both what I need to write and for both what I need to read. And I go through all my operational transaction. And just before I'm ready to commit, so I've done all the operations, I've done all the read, I've done all the computation, I know exactly what I need to write down, I know the changes that I need to do. Now I just want to finalize it. I just wanted to commit it. Just before I do the commit, then I do a certification phase. And what that certification means, I want to be able to certify my rights. That means anytime for a right, if I had held a shared lock so far, and I held a shared lock just because to allow other readers to continue, because if for something that I want to write, I get an exclusive lock, then I'm basically blocking everybody. But if I have got just a shared lock, allowing other readers to read the data, just before the commit, I'm going to certify my shared lock. And what the certification means upgrading my shared lock to an exclusive lock. What does upgrading my shared lock to exclusive lock means is that I can only get an exclusive lock if there are no readers, because I'm getting an exclusive access. So I start by getting everything shared. Just before write, I enter a certification phase. That certification phase, it converts my shared lock to exclusive lock for things that I wanted to write. And that certification can only succeed if there are no outstanding reader. And if the certification does succeed, then I can go ahead and commit. So that's the idea. So now think about it. We have only 3 minutes. We're going to continue this next time. But can you think of why is that beneficial, or why is that interesting potentially, or why is that correct potentially? So kind of hear your thought on this.
So we're increasing the time we can read the data.
Increasing the time that we can read the data, absolutely, because this whole time, instead of just locking everybody out, we say we're just going to hold the shared lock. And that idea could be thought of as inherently optimistic, because, and this is where the optimism come into the play. The optimism is, I'm just going to start getting a shared lock. But then I kind of assume by the time I get to my certification phase, if there were any outstanding reader, they're kind of done. I can certify and I can commit. So there is an optimism in it. So optimistically, I'm only just going to get a shared log. And optimistically, I'm going to say by the time I get to the end, I know there are no other potential rider right now because, well, I mean, I assume there's no other potential rider. I mean, I wouldn't know at that point anyway. But I say, okay, maybe potential readers, I'm the only rider. I've already read, I've already also do have a shared log, so I know other people cannot change what I've read. And I kind of assume by the time I get to the certification, any readers that are there, they will be done. I can certify and I can commit my changes. So I really reduce the duration of my exclusiveness to the data to this between the certification phase and my commit phase. And my computation phase to figure out what I need to do, what I need to read or write, it could have been a much longer period of time. So for that long duration, there is no conflict, there is no clashes. Everybody can sort of successfully coexist and read the data. Only during that final phase of that certification, I get an exclusive access, reduce the concurrency, make sure that my right is not going to have any right-right conflict, make sure my right is not going to violate any repeatability of the other readers. And if those are satisfied, then I go ahead and get my exclusive log and then finalize the transaction. So I kind of leave you with that. And then we kind of talk about what is the next step for this 2BCC concurrency, looking at how to make it more optimistic, what aspect of pessimistic, and then also look at how does this map to the indirection? How do you can implement this idea inside that indirection? Okay. Any other questions? Okay. Have a wonderful day.